Okay, we resume this mathematical physics section. So our next speaker, I again will introduce him, Philippe Di Francesco. Brief introduction, got his PhD 1989 from Paris 6 and 2004 his habilitation. Major progress was Paris 7 and as various prizes, Prix Rivaux, Poincaré Prize, well, there are various Poincaré, so this one is from the French Academy. Laplace Medal, working in Saclay, but spent time in various states in the US, in Germany. I will not waste his time listing all that. Many papers, about 100 I think, in statistical physics, in integrable system combinatorics. Will not steal more of your time. So Philippe Di Francesco.
Thank you for the introduction. I thank the organizers for this invitation. And I'd like to start by thanking my collaborators in recent years, and especially Rinat Kedem, Emmanuel Guiter, and Paul Zinjustin, the first three on this list, work of which I'm going to report now. So this is an extended list of collaborators in less recent years. Okay, so my title is Integrable combinatorics, and so I should start with the title. What the heck does it mean? So I'm going to start with the word integrable. So what do I mean by the structures of integrability? So I've tried to make a sort of distinction on the one hand between continuous and discrete formulations of integrability, and on the other hand, classical quantum and non-commutative. So the way I like to think of integrability is really an avatar of the symmetries of the systems you're considering. The more symmetries, the more chances it has to be integrable. And to be more precise, the classical notion of integrability is called Weyl integrability, and states that essentially there's sufficiently many conservation laws in your system that you can actually solve it, okay? So that's original formulations in the continuous, and in the discrete, well, you have to think of discrete differential equations, so it's difference equations, or recursion relations, if you prefer. And we will find out that one of the very nice places to look for integrability in discrete equations is cluster algebra, okay? So you've heard of cluster algebras a few times during the plenary talks of this conference, especially in Kashiwara's talk earlier today. All right, so from classical to quantum, so the quantization here, first in this formulation is quite natural. There is such an object called quantum cluster algebra. On the continuous side, I like to think of quantum integrable systems, systems with infinite number of symmetries. And one of the formulation of this infinite number of symmetries is infinite numbers of commuting transfer matrices guaranteed by the famous Young-Baxter equation, which is kind of a source of all these systems. And it has a lot of underlying algebra, in particular structure of Hecke algebra and quantum groups. Okay, and now if you go one step more to the non-commutative setting, well, you have to think of what were the tools or the structures that were crucial in order to make things work in those systems. And there's a very important object, which is the determinant. So thanks to Retak and Gelfand, we know now that there is a very natural and very beautiful formulation of determinant in non-commutative settings called quasi-determinants, okay? And using quasi-determinants, people have been able to make sense of lots of the classical integrable equations in terms of non-commutative variables. And of course, the last step would be to promote cluster algebras to a fully non-commutative setting, of which some steps have been done. So far so good for integrability. And now I pass to combinatorics. So I'm going to describe tools of combinatorics adapted to certain combinatorial problems. So the combinatorial problems, I distinguish between the path of tree problems and the problems involving extended two-dimensional objects like tilings, alternating sign matrices, lattice models, random lattices. And I distinguish between various types of combinatorics. So purely enumerative, you count. Algebraic, you look for algebraic structures that help to count. Asymptotic, you take limits. And then quantum and non-commutative again. All right, so I filled my boxes with those notions. So you want to enumerate path, and a very natural tool is continued fractions. You want to enumerate tilings, lattice models, dimer problems. Determinants are the most useful tool. The algebraic formulation of paths or trees involve theory of orthogonal polynomials, so very algebraic object. Algebra underlying these two-dimensional lattice models, especially when they are integrable, is the better ansatz and possibly cluster algebras. Asymptotic enumeration, we know a lot about, well, asymptotics of paths, essentially Brownian motion and continuous random trees for trees. For these two-dimensional extended model, field theory, which is really a tool of physicists, has been extremely useful. And a tool that started being from physicists and now has derived into mathematics is matrix integrals. And now going over to quantum or non-commutative, well, continued fractions actually can be really easily promoted to quantum and non-commutative objects. There's also a theory of non-commutative continued fractions due to Gelfand and Retak. And cluster algebra, same thing. All right, so in this talk, I'm going to, rather than try to make the theory of everything, give you examples, okay, and take you through a list of examples. And so my examples first will come from the physics of quantum gravity and be essentially Lorentzian gravity and Euclidean gravity in the form of Lorentzian triangulations and planar maps. Then I will go over to objects that are kind of suggested by integrable lattice models, and they will have all these very nice acronyms: alternating sign matrices, descending plane partitions, totally symmetric self-complementary plane partitions. Finally, the last objects I'm going to look at are also borrowed from lattice integrable models, but in the form of quantum spin chains. And it will be much more algebraic, and we're going to be interested in computing graded tensor product characters of certain algebras, and we'll see a deep connection between cluster algebras and this stuff, and also paths, whether classical, quantum, or non-commutative. So that's the program. And just show you that the relevant words are here: trees, paths, and all these objects. Okay, so I'll start with Lorentzian gravity. So the idea is to have a discrete physical system to understand interactions between matter and the underlying space-time. So the space-time will be just a discrete space-time, which you can think of as triangulations, okay, with space in one direction and time in the other direction. I'm doing the thing in 1 + 1 dimension. So the randomness of the space-time, so the fluctuations, if you want, of the space-time will be simply given by these triangulations of slices, time slices. So it's a lattice in time direction, but it's a random lattice in space direction. So I want to consider those objects and try to see what they have to tell me and try to compute things like partition functions, correlation functions. Okay, so the first remark here is that you can go over to the dual. And the dual is rather simple to formulate, so let's even forget about the original problem and just look at this. It's a sort of random brick wall. So the dual is a trivalent graph, okay? And so if you squeeze a little bit things, I don't have time to explain how to squeeze, but if you squeeze things a little bit, you end up with a tree. So in fact, Lorentzian random triangulation is just a tree in disguise. Okay. So let's go back to the triangulations. How to count such triangulations? Okay, so there's a very simple tool of statistical physics, which is called the transfer matrix. So you look just at the evolution of this, and you think of it slice by slice. How do I go from one slice to the next? Well, there is a transfer matrix, and essentially it's a matrix with matrix elements between two states, okay? And here my state is going to be just labeled by the number of half edges entering and half edges outgoing, I and j. And I form the matrix of all the possible combinations here. So all the arrangements of top bars among all the bars is just the binomial coefficient, right? So Tij is just an infinite matrix with ij and z plus and with binomial coefficients. Very simple transfer matrix. Now, if I want to make it a little bit more realistic for my purpose, and my purpose was to really investigate quantum gravity, that is, the effects of curvature and area of those surfaces, I should introduce some curvature and area terms. So curvature is just something that is going to count, let me see if we can see that here. So let's concentrate on these three up edges here. You see that they correspond to three triangles which all point down. That is, this point here has quite a lot of curvature. So the curvature at a point is really proportional to how many triangles you can have sharing the same vertex there, right? So I want to put a curvature weight which is proportional to how many triangles point to the same vertex like this. And that's this weight up here. So for each two consecutive such down pointing or up pointing triangles, I put a weight A. Okay, so there's a weight A which tells you something about the curvature, and then G per triangle, so dually G per vertex. Now, my binomial coefficients, it's very easy to see, split into a sum over binomials like this, and it becomes a polynomial of A inverse and G. Now, a very nice way of looking at this formula is to just consider its generating function, infinite generating function, and here, miracle is just a rational fraction with extremely simple denominator. Okay, so when you multiply two such transfer matrices, for instance, you just make the convolution between these generating functions. And the property of convolutions of rational functions of degree, denominator of degree less or equal to 1, is that it's closed. They close under convolution. So there's something very simple happening. And here is my first example of quantum integrable system, which is that any two of those transfer matrices commute provided the parameter G and A lie on some variety, okay? And that's the definition of this variety. So whenever this thing is a constant, right, you take any pair GA that satisfy the same equation with the same constant, the corresponding transfer matrices will commute. So we get an infinite number of commuting transfer matrices. Now, just from this remark, you can very easily diagonalize this transfer matrix, compute correlations, basically do all the job that the physicists want you to do in order to understand the theory. Okay, so let me go now to the second example, which has to do with Euclidean gravity. So Euclidean gravity is just a version in which there is no specific time direction, right? The space-time is just two-dimensional. So one useful way of thinking of it is you start with a lattice model, right? A model defined on the lattice. And then you randomize the lattice, right? You add a fluctuation of the underlying space, which is exactly the idea of quantum gravity. And now you tessellate some surface of arbitrary genus, let's say, and you use the same statistical model that you put on the random surface, okay? So there was a big boom in understanding those systems in the 90s. So there's all these people involved who understood how to compute correlations and partition functions, etc., for these models in terms of random matrices. So the exact solutions found via random matrices give you really a discretized version of quantum gravity, and then you have to take limits and a whole host of interesting things have been discovered, all related to one or the other notion of integrability. So in particular, let me summarize it this way. if you have a matter theory here, the most general matter theory will have parameters, right? Matter parameters. Now, in the space of parameters, you will have commuting flows. That's the integrability in this case. Now, a number of questions were left unanswered by this approach by matrix models, and one in particular regards intrinsic geometry of those random surfaces. And the question really is that of correlations, right? So you want to find, to say something about surfaces in which you mark, say, 2 points, and you impose that their geodesic distance remain fixed. Okay? What can I say about that? And it took a long time, and it's not until 2000-something that we were able to solve that problem. So first, we need a model for discrete random surfaces. So let's look at we start with a quadrangulation, so made of squares glued to each other, right? And then the dual of that is just a tetravalent graph. So let's say it's planar, genus 0, tetravalent, and then we want to say something about distance between points, so let's take 2 legs, okay? Now, in this situation, if I want to define the geodesic distance between those 2 legs, I can say it's the smallest number of edges I have to cross in a path going from one to the other. So here it's 2. Okay? So Schaeffer, in '98, came up with a beautiful bijection between these random maps and what are called blossom trees. And let me describe it very quickly. So you have a pair of scissors in your hand, and you walk around the external face of your map, okay? You're going to cut whenever you can without disconnecting the map. So you do a first round, and so once you finish the first round, you have cut here 4 edges, and now you continue, you do a second round, but now you can go inside, and you can still cut, etc. And the process stops when you can't cut anymore. So the result is a connected, of course, because you never disconnected anything, tree, and it's called a blossom tree. So now, for counting the number of such objects with specified distance between the 2 marked points, you just have to count those objects, which are just trees with small decorations. And that can be done. And you find, after thinking a little bit about it, a very nice discrete recursion relation, where n is this geodesic distance. So the definition of Rn was not specified distance, but distance less or equal to n. That's what makes it work. Now, what's so special about this recursion relation is that it's integrable. So discrete integrable, what do I mean by that? If you had a differential equation, say, of order 2, then a first integral would be saying that you can integrate it and have a first order quantity equal to a constant, right? Well, here it's the same thing. You think of this as a difference equation of order 2, and there is a primitive, if you want, of this equation, which involves only 2 neighboring r's instead of 3, like here, such that the difference here is 0 modulo the equation. Okay? So conserved quantity. Now, the existence of this conserved quantity is extremely crucial to solve the problem. And actually, we came up with a solution involving, some of you might recognize, the same structure as the solitons of a KP hierarchy as exposed and computed and understood by Jimbo and Miwa. So this would be a 1 soliton solution. So this is the exact solution of this recursion relation here, where x has to be one of the roots of this quadratic equation. Now, once you've solved things explicitly, you can say all sorts of things. In particular, you can prove that the fractal dimension of quantum gravity is 4. You can compute scaling function, and there's a whole bunch of works, related works in probability that have continued this work. All right. So let me go over to my other set of examples, which now, instead of having random lattices, have fixed lattices. Okay, so quantum integrable systems on fixed lattices. So I'll start with the archetype of the integrable lattice model, which is this 6-vertex model, and actually the ICE model. So, so essentially, it's a model on the square lattice, on the edges of a square lattice, where you put random orientations, left or right, up or down, in such a way that at each vertex you have 2 entering and 2 outgoing edges. If you were at Rick Kenyon's talk, he discussed this very same problem. So this was solved by Lieb in '67, beautiful solution. And that's my first object. But the second object was invented by Robbins and Ramsey in '82, totally independently, with something completely different in mind, which was trying to generalize the notion of a determinant and keep certain of the properties of a determinant, okay? And the determinant, as you know, is a sum over permutations, right? So they wanted to extend the set of permutation to something a little bit bigger, which would allow for some interesting properties. And they came up with a definition of alternating sign matrices. So you see an alternating sign matrix is almost like a permutation matrix, but instead of having a 1 per row and column, you also allow to have -1s. And the rule is that whenever you have a -1, there should be a 1 somewhere on its left, and a 1 somewhere on its right, and a 1 somewhere below, and a 1 somewhere above. It's protected by 1s. So that's these alternating sign matrices. And it took a while before people realized that, in fact, these two are in bijection. Okay? So we have the same object here. Now, another part of this story is called the totally symmetric self-complementary plane partitions. You also saw some plane partitions if you went to Rick Kenyon's talk. Now this plane partition, so it's a rhombus styling of a regular hexagon, if you want, which has all the possible symmetries of the hexagon. Okay, so there's only 1/12 of the hexagon, which is the fundamental domain under these symmetries, and that's called a totally symmetric self-complementary plane partition that was introduced by Andrews in the '70s. Okay. A third object is called a descending plane partition. This is not the original definition, but it can be transformed into an object like this, which is again a tiling, rhombus tiling, of an almost regular hexagon, but with a central hole here. Okay? And with symmetries, which are not all the symmetries, but just a symmetry of rotation by 2 pi over 3. Okay. Now the remarkable thing is that all these objects, alternating sign matrices, descending plane partition, totally symmetric self-complementary plane partitions, they are all enumerated by the same number. The count is the same. So there's this beautiful proof by Zeilberger. So Zeilberger just took the north face. He showed essentially that this number is the same as this number directly with generating functions. Kuperberg was smart. He showed that these two things are in bijection, so he used all the results that the physicists had on this. And there was a conjecture of Mills, Robbins, and Ramsey formulated around '83, which we finally proved in all completeness with Berendt and Saint-Justin. Okay, so now, where's the physics? So there was physics, of course, involved in this 6-vertex model. But there is a big puzzle, because nobody understands to this day why these 3 sets of objects are enumerated by the same number. There's no bijection node, okay? So I think what physics did here is provide with the missing link. And the missing link is called the loop model. So the loop model is just a model on a semi-infinite cylinder, right? So it has a boundary here. And you draw at random on it. So you wrap a square lattice on there, okay? Say of perimeter 2n in this direction, and you draw at random these 2 pictures on each of the faces with probabilities p and 1 minus p, p being strictly between 0 and 1, okay? And you look at asymptotic configurations, so which boundary links are linked to which boundary links in asymptotic configurations, and you get relative probabilities for those guys. And actually, this system is also an archetype of integrable system, and it can be solved by means of what is called the quantum Knight-Zamarchikov equation and its solutions. So there's a bunch of people involved here, and there was a famous conjecture relating some refined enumeration of alternating sign matrices and configurations of the ground state of this model, finally proved by Cantini and Sportiello in 2010. Okay, so I'm saying that this provides a missing link because certain refined enumerations here correspond to this, and other refined enumerations correspond to that. Okay? All right. So, and the cherry on the cake was something we weren't expected a priori, but with Zin-Justin, and there was also some papers of Knudsen and Zin-Justin, we found that the variety of matrices of vanishing square, actually its equivariant cohomology, was in fact also a solution of a QKZ equation which could relate to a refined enumeration of those objects. Okay? So some very nice interplay with all sorts of problems here. So I want to give you a feeling of how this works, and here it is. So you think of these configurations, asymptotic configurations, as being, in fact, a vector, right? Think of it as a vector, and now I want you to think of adding up one more row to that picture as an equation of an operator on the vector equals a vector, t psi is psi. So psi is actually the ground state, the fundamental state of this T operator, which is actually the transfer matrix of a loop pendant. And this transfer matrix is made of little pieces, which are called R matrices, and which involve the generators of a temper-Lilib algebra. Okay? So that's the first part. The second part, okay, is what about this R matrix? It satisfies the celebrated Yang-Baxter equation, which essentially is telling you that you can move around lines across intersections. Okay? So now I come to my QKZ equation. It comes from just considering my ground states, acting with an R matrix on it, and then applying iteratively this relation to push this up to infinity. And at the end, I have absorbed completely my R matrix, but I have interchanged these two lines. So the R matrix acting on the ground state interchanges two variables in the ground state. Okay, that's the QKZ equation. Therefore, the quantum integrability here provides the missing link between all the mysterious enumeration results, because by solving these QKZ equations, one actually has a perfect grasp of the entries of a ground state, and one can, of course, compute various sum rules, etc., and do, in a bunch of works, we found relation to SSSM, TSSCPP, DPP. Okay, so my fourth and last subject is these graded tensor product multiplicities. So the setting is the same as before, but slightly more general. So we are still looking at quantum spin chains, okay? So defined on tensor product of vector spaces here, but the R matrix I'm considering is much more general. It's called inhomogeneous because you don't have to choose the same representation at each point, okay? So these spaces here are actually modules of a Youngian of any Lie algebra G, and so these are modules with certain properties which make the whole story be nice. So you can think of a step zero of all this as being done by Bethe in 1931 in his groundbreaking paper Zur Theorie der Metallen, in which he treats the case G equals SL2, which is all these representations are two-dimensional. Okay, so my state space will be just these tensor products of Kirillov-Reshetikhin modules. There's a natural grading found by Kirillov and Reshetikhin in '87, which uses some sort of linearized energy function, and which really came from the combinatorics of the Bethe ansatz solutions to this quantum spin chain. So since this grading has been understood in various ways, and I'm going to present to you yet another way today. So I'm referring here to Feigin and Loktev for something they coined the fusion product. So we want basically to compute Hilbert polynomials of characters of these tensor products with respect to the grading. Okay, so I decompose the tensor product into irreducibles. I have Q multiplicities, which is just a polynomial of Q, and I multiply by a character of the irreducible. All right, so in the classical case, Q equals 1, things are very simple. The KR modules are indexed by two indices, alpha and I, which correspond to an irreducible representation with rectangular Young diagram. And my tensor product is therefore a product of a bunch of those guys with multiplicities n alpha I. So instead of writing all these modules, I just write n. Okay. So another definition, the Q system for the Lie algebra G is a system of nonlinear recursion relations of the following form, which are dictated basically by the structure of a Cartan matrix of the Lie algebra, right? So here you have terms which are self-explanatory, but here it's a product over the betas which are connected to the node alpha in the Dynkin diagram, okay? Now, what's so special about this system? It's discrete integrable, okay? So we prove that with Rinat Kedem. And a second thing which is special about this system is that it's actually satisfied by the characters of the Kirillov-Reshetikhin modules, provided you define, of course, the zero character as being the trivial character, which is 1, and these guys are the fundamental characters. So here is the most simple example. It's when my Lie algebra is SLN, then the fundamental character is just the Schur functions for a vertical strip, which are just the elementary symmetric functions, and the Q alpha A, K are the Schur functions for rectangular Young tableaus, and they satisfy this beautiful relation, which is the AN-1 Q system. Okay, so we came up with a theorem which allows to compute characters in terms of solutions of the quantum of a Q system here, which says that there exists a linear functional which goes from the algebra of solutions of this Q system with specific boundary conditions to symmetric polynomials in which, well, the image of the particular combination here with the multiplicities of Kirillov-Reshetikhin characters gives me the desired character. So that's at Q equals 1. But there's a version at Q equals Q. But for that, I have to explain to you the connection between this Q system and cluster algebras. So the Q systems are naturally associated to cluster algebras. So as we've seen earlier today, a cluster algebra is essentially coded by a quiver or a skew-symmetric matrix, which codes the quiver, and variables at each vertex of the quiver. Okay? So here is the adjacency matrix of the quiver in terms of a Cartan matrix of the corresponding algebra. And I give you the example of A5 here, and also of D4. So you can really see the Dynkin diagram up here and the Dynkin diagram down here, and then connections between them. The cluster variables are just variables at the vertices, and they look like this. So these quivers have appeared already in the physics literature, in the SUN Yang means theories, the Seibert-Witten curve, and n equals 2 supersymmetric gauge theories. Okay, quantization. So the advantage of having connected our problem to cluster algebras is that for free we get the quantization. Berenstein and Zelevinsky have provided us with a quantization scheme for cluster algebras, which is quite general, and so we can define a quantum Q system here. So kappa is the quantum parameter, and now you see that the variables are promoted to operators in a sense because they no longer commute, but Q commute or kappa commute. Okay, and if we take Q related to kappa via the determinant of the Cartan matrix, then we find out that this is going to give us exactly the grading we wanted. So the quantum of a quantum cluster algebra gives the quantum deformation which is necessary for the graded characters. And here is the theorem. So it's exactly the same theorem, but now with non-commuting objects, okay, and the full character. Okay, so you can really think of these Q alpha I non-commuting variables as a sort of non-commutative deformation of a Grothendieck ring, right? Because they are characters, but objects that don't commute anymore. Okay, so to just make you understand what's going on, let me just give you the example, the full example of SL2. So here is the Q system for SL2. Those of you who love Chebyshev polynomials will have recognized one of the relations satisfied by Chebyshev polynomials. Anyway, the cluster algebra related with this recursion relation is the following. It's essentially, the cluster algebra associated to a difference equation is essentially thinking of the various Cauchy data that I can consider for my system. So a Cauchy data is just, what do I start with? Well, I start with Q0 and Q1, or maybe with Q1 and Q2. I have to start with two consecutive values, and then by using my recursion relation in one direction or the other, I get all the others, right? So the cluster, in the cluster algebra, is really just a pair of consecutive values of Q in this case. And a mutation of a cluster algebra is just what makes you go from one pair to the next. So here Q0 is promoted to Q2 via this formula, whereas Q1 remains the same. Or if you go in the other direction, Q0 remains the same, but Q1 becomes Q minus 1 via this formula, etc. Okay? So I think it's a good way of thinking of a cluster algebra. Now, integrability. So why do I say that it's integrable? Well, if I take a more general solution to this system, then it obeys a certain equation, which is that this quantity is constant, modulo the system. So just like in my quantum gravity example, where we had the first integral of our equation, same thing holds here. Okay? So now, what do I do with that fact? Well, that fact by itself allows to solve. So if you define these three quantities in terms of my initial data Q0, Q1, okay, then you find that the conserved quantity is just the sum of the three. And also you notice that Y1, Y3 is also equal to 1. And it's very easy to compute the generating function of a solution of a quantum Q system in terms of Q0 and Q1. And it's given by this continued fraction that stops. So in fact, there is a description of Qn as a partition function for paths on a segment of size 3 here, with certain weights when you go away and certain weights when you come back of your paths. So that's where paths and cluster algebra intersect. Okay? Now, the mutations of a cluster algebra can be understood as rearrangements of a continued fraction. There's a beautiful little lemma which allows to rewrite A over 1 minus B over 1 minus C as A prime plus B prime over 1 minus C prime, and which you can understand in terms of graphs as being counting the paths on this graph is the same as counting the paths on these graphs, provided the weights are related via cluster algebra relations. Okay? So, quantization. So the quantum Q system for SL2 is here. So now you notice that Qn and Qn plus 1 no longer commute. Okay, so essentially it's still integrable. We can still show that there is a conserved quantity C here, which is given by this, and which is still expressed in the same way in terms of Y1, Y2, Y3, except that here I have to be careful about the order in which I write things. And the same solution works. So we get quantum paths without even thinking about it. And this goes over to non-commutative settings. All right, so let me come back now to my graded characters and try to understand better what this graded character look like. And to that end, I'm trying to understand what happens if I add up one more space to my chain. Okay, so let me add up Kirillov-Reshetikhin beta k module to my chain. Okay, so according to my previous theorem, I have this linear functional. And now the question is, can I represent adding one more object here as a certain operator acting on chi to give a new chi? And the answer is yes. And the answer is really beautiful. It's yes in the form of a difference operator, d beta k. So adding the beta k Kirillov-Reshetikhin module to the character just means multiplying, acting on it by this difference operator. So these are rational functions of z. And here we have shifts of the ith variable by q. So a subset of beta elements of one n is going to be shifted in this operator. Now, if you have any knowledge about McDonald polynomials, this looks very much like an operator out of McDonald theory. So this operator satisfies the quantum Q system. Okay, that's the first theorem. Second theorem is that the characters now by iterating are just obtained by iterated action of those operators on the constant 1. But more than that now, there is a natural T deformation of all this. Why? Because if you know a bit about McDonald theory, you know that the McDonald polynomials are common eigenfunctions of McDonald operators, which are actually given by this formula. So it suggests to modify slightly this definition and make it look like this. So why? Because the operators that we found had an index k, here there is no index k, which was precisely given by some insertion of powers of x inside a very analogous expression. So these guys, they satisfy the fact that the limit t going to infinity, so I blow up this term, and I end up with my previous operator. Okay, so the limit t going to infinity of those guys is our guy. So let me now ask the question, what's the algebra of these more general operators? And there's two answers. First answer, thanks to Cherednik, who did the double affine algebra theory, these M alpha k's are actually a certain iterated action of SL2Z action of the double affine Hecke algebra on the McDonald operators. The second answer is thanks to a homomorphism between the elliptic hole algebra and the so-called spherical double affine Hecke algebra, one can also formulate these operators within the framework of elliptic hole algebra. And essentially, what we end up seeing is that the elliptic hole algebras are a natural T deformation of the Q system quantum cluster algebra. Okay. So here is a summary of what I tried to convey. So we've seen various formulations of this integrability, both in discrete and continuous settings. Okay, and it was not obvious, by the way, whether a discrete system could display continuous integrability and vice versa. Okay. We've seen the central role played by cluster algebras, and a little bit of a role played by paths. Another formulation which is equivalent to that of paths is that uses dimer models, and there's this beautiful paper of Goncharov and Kenyon in which they create a whole class of cluster algebras which are also discrete integrable. And finally, my last remark is that these combinatorics, they survive beyond quantization, okay? So, and the deep reason why things survive beyond quantization is because there are these path formulations. And there's nothing better than a path to give you a way of understanding how to go to things that don't commute. Because a path takes steps in a certain order. So if you put weights at each step that don't commute with each other, it still makes sense as a path, okay? And so, in fact, I could go beyond that and say that the combinatorics of paths is naturally formulated in terms of non-commuting variables. Okay, so for quantum things, there is an object which we have found, which is the quantum determinant. Let me maybe finish with that. So the quantum determinant is like this. So first of all, I remind you the Q system for type A that we saw several times. And here I remind you of a very nice formula, which is called Denano-Jacobi identity on minors of any matrix. So you take a square matrix, alpha plus 1 by alpha plus 1, takes the determinant. Now multiply it by the determinant of the same matrix, but in which you remove first row, first column, last row, last column. Then it's equal to the product of determinants like this minus product of determinants like this. So this is the Lewis-Carroll identity also, which is used in condensation of determinants. And now, if you take for Q alpha n the Hankel matrix of the Q1n, defined like this, then it satisfies, thanks to this relation, the Q system for A type. So it means that the classical solution is just given by Hankel determinants, the Q alpha n, the Hankel determinants of Q1n. So what happens in the quantum case is that, so you have this new system, right, with non-commuting variables, right? So you can still think of it as a sort of quantum de Nano-Jacobi relation, okay? And here is the theorem we came up with, which is that Q alpha k can still be expressed in terms of a Q1n via these generating functions here as a homogeneous polynomial of degree alpha, but here you have a certain kernel and you're supposed to take a constant term. So let me just explicit it in the case of 3×3 Hankel matrix. The Q determinant of this 3×3 Hankel matrix gives me Q3n, and here is what it is explicitly. And here we notice that it's a sum over alternating sign matrices of size 3×3. So actually our quantum determinant is nothing but a certain formulation of a Mills-Robbins-Ramsey determinant, deformed determinant, by means of which they define the alternating sign matrices. So with this last remark, I will finish by just saying that many of the things I have described go over to non-commutative settings. There is such a thing as the non-commutative A1Q system, which was a while ago conjectured by Kontsevich to have integrability and nice solutions, and which we worked out with Rinat Kedem. And ever since, progress has been made on the front of non-commutative stuff, in particular by Berestein and Retak, who define non-commutative surfaces, which are a non-commutative version of one of the largest classes of cluster algebras, which are cluster algebras attached to surfaces. Thank you.
Okay, thank you for your nice talk. It's now time for questions. Yes.
Thank you. I would just be curious to know what a non-commutative continued fraction is.
Yes.
Can you say a word about that?
Yeah, so I can show you very quickly. Actually, yeah. I have the example of the A1 quantum Q system just after that. Okay, so this is the A1 non-commutative quantum Q system. You see, you have to put things in a certain order, but it's essentially the same equation, but now with non-commutative variables. Okay, so now the integrability means there are two conserved quantities instead of one. So things are slightly different than in the classical and quantum case. But the really impressive thing is that if I still define y1, y2, y3 like I did before, but with these non-commuting variables now, fully non-commuting, then k and c are still given by the same expressions, okay? Therefore, I can write these generating functions of the solutions as a non-commutative continued fraction that stops, okay? And the interpretation of this thing is just the same paths as before, but now with weights y1, y2, y3, which are non-commuting variables. So it's really the straightforward formulation. And if you remember, I had shown you a very nice rearrangement lemma of continued fractions, which allowed to understand mutations. Well, the same lemma holds for non-commuting variables. So there is, in principle, also the understanding of what should a mutation be in terms of these rearrangements.
Okay, are there more questions? I see none, so I propose we thank Philippe, and since this is the last talk of mathematical physics session at this Congress, so let's thank with him to all the speakers.